Hey everybody, welcome back for Thermodynamics Continued, our thermo lecture number 2. In this lecture, we're going to talk about how enthalpy and entropy together help us determine whether or not a reaction is spontaneous. If you recall, a reaction is favorable or more likely to be spontaneous if it is exothermic, and if it increases in disorder, entropy. Now, it doesn't have to be exothermic and it doesn't have to increase in disorder in order to be spontaneous. So we are going to take a look at how these two factors both combine and relate to one another in order to determine spontaneity. So the guy who figured that out, the relationship between delta H and delta S, was a guy by the name of Gibbs. And so he defined a new state function called Gibbs free energy, delta G. So this stands for Gibbs free energy. And Gibbs free energy is measured in kilojoules per mole, just like delta H is. And it's a state function, just like delta H and delta S, where you can actually just subtract your final state and you can subtract your initial state from your final state to get the amount of free energy change in a reaction. And we don't need to derive this equation, but what Gibbs figured out is that the total free energy change in a reaction is equal to the change in enthalpy of the reaction minus the temperature times the entropy change involved in that reaction. And so this is a very, very important equation. This is the equation we're going to go back to every single time to help us determine whether or not a reaction is spontaneous, based on how endo or exothermic it is, and based on how much the order and disorder of that system changes. So we need to talk about signs of delta H. No, not delta H. We need to talk about signs of delta G and determine or assign whether or not those signs make a reaction spontaneous or not spontaneous. When you have a delta G that is less than 0 or a negative delta G, that means that the reaction is spontaneous in the forward direction. And then again, of course, if it's spontaneous in the forward direction, it is not spontaneous in the reverse direction. So if you get a positive delta G, that reaction is not spontaneous. And if you're wondering, how do we get those signs? Why is it that a spontaneous reaction has a negative delta G? Let's talk about, we can actually sort of derive that. We can figure out, based on this equation, why it would be the case that a negative delta G would be spontaneous. So let's take a look at that. Remember we said that spontaneity is favorable when something is exothermic? So that would be like a negative delta H. And when it has a positive delta S. Do you guys see here, up here in our equation, if we have a negative delta H and we subtract the temperature in Kelvin, of course, so there's not going to be a sign associated with temperature. So we're going to subtract from that the temperature times a positive delta S. Do you guys see how just algebraically, if we have this negative and we're subtracting this positive value, that's the same thing as adding a negative value? So if that was the case, we are always, when something is exothermic, if something is exothermic and increasing in entropy, the reaction is always going to have a negative value over here. So that reaction will always be spontaneous because this is favorable, exothermic is favorable, and an increase in entropy is favorable. So that's why a negative delta G will always result in a spontaneous reaction. Conversely, we could look at what would happen. Maybe I should change my pen color. Come on. Oh, I think I have to do this. Okay, maybe we'll look at red. Here we go. What would happen if we had something that was not favorable? For example, if we have a positive delta H and a negative delta S, those are not favorable conditions. If we have a positive value here and we subtract from that the temperature and a negative value, that's the same as adding a positive. So this algebraically will always result in a positive delta G. So you can see here that a positive delta G will result in the reaction being not spontaneous. Now, I'm sure you're wondering, well, what happens if you have like a positive delta H and a positive delta S, or a negative delta S and a negative delta H? We'll get into that later. Of course, that's going to have to depend on temperature. But anyway, I'm getting ahead of myself. Okay, so back to signs for delta G. A negative delta G, the reaction is spontaneous, and a positive delta G, the reaction is not spontaneous. And if we get a delta G that is equal to 0, that means that the reaction is at equilibrium. So one way that I like to think about spontaneity is sort of like a ball rolling down a hill, right? So if we were to start, and there's some great diagrams in your book for this on page 804. So when you go read, pay attention to those figures. If I start with a ball up here on this side of the hill, it is going to spontaneously roll down the hill that direction. And of course, we know it's going to go back up a little bit onto the other side, and it's going to settle. It's going to go back and forth, back and forth, and back and forth, and settle down here at the bottom of the valley. So it's going to spontaneously roll in that direction and settle down there. Down here is where you would consider your reaction to sort of be at equilibrium. Now, we of course know that means it's going in the forward and the reverse rates at equal rates, and it's just going to keep doing that, keep doing that, keep doing that. That's not going to happen with a boulder on a hill. But in terms of a reaction, you know, products turning into reactants, wrong direction, reactants turning into products, products turning into reactants, going back and forth at equal rates. That's what we mean when we say that we are at equilibrium. So here is where your delta G is equal to 0 when your reaction is at equilibrium. You could also think about it as the ball starting off on this side, starting off with all products, and the products spontaneously going in the reverse direction to turn into reactants. And again, that reaction is going to settle out at equilibrium. Okay. This diagram just, highlighting for you guys how reactions can achieve equilibrium from any direction as long as you have both reactants and products present. Okay. So let's practice actually quantitatively. Here we were talking sort of qualitatively about what it means for a reaction to be spontaneous. Let's actually quantitatively calculate whether or not a reaction is going to be spontaneous based on a known enthalpy and a known entropy. So here we go. We have this reaction of nitrogen reacting with oxygen to produce nitrogen monoxide. And based on this delta H, which is a positive value, we know that this reaction is endothermic, not super favorable in terms of spontaneity. But it has a positive delta S, which means it is increasing in disorder, which is favorable. The question is, I have something that's not favorable, something that is favorable. Is this reaction going to be spontaneous or not? It's going to depend on the magnitude of these two values and the temperature at which this reaction is occurring. So all I have to do is just plug these values in to my delta G equation. Delta G is equal to delta H minus T delta S. And then you just got to watch your units, you guys, right? So my delta H is in kilojoules, so I've got 180.7 kilojoules minus my temperature, 298 Kelvin. And I need to turn my joules per Kelvin into kilojoules per Kelvin here for my delta S so that my units work out. So I'm going to be at 0.0247 kilojoules per Kelvin. And if I do my math correctly, I get 173.3. This is going to really stink, you guys, because if I write something wrong, there's nobody here to correct me. Kilojoules. So with this positive value for delta G, this reaction is not spontaneous in the forward direction, as is written, right? The reaction would be spontaneous in reverse. So like the decomposition of this reaction at this temperature is spontaneous, but the synthesis of this substance is not. Okay, great. Hopefully that math is right. Moving on. What did I want to talk about next? Oh, yes. Okay, this is like your most common way of sort of thinking about free energy, which is like, how endo or exothermic is it? How ordered or disordered is this reaction? And, how will those compile into helping us determine whether or not this reaction is going to happen on its own? However, we can also use delta G's, just like we used delta H's and delta S's, as standard values, okay? So when I look at, this variable right here, again, remember this not symbol is for, is referencing standard conditions. Standard conditions being, like we said before, 298 Kelvin, 1 atmosphere of pressure. And if we were talking about solutions, which is going to be important to us when we talk electrochem, standard conditions for solutions would be 1 molar. So that'll be important later on. Just remember, 1 molar, 1 atmosphere, 298 Kelvin. So free energies of formation are just the free energies, like the amount of free energy that a substance has. Or the formation of that substance, like how much free energy change there is associated with the formation of that substance. Now, of course, when we're talking about things that are being formed, those values for elements in their standard states are 0, right? Because all of these elements were formed during the Big Bang, so we don't have a measured free energy change for the formation of, let's say, oxygen gas. So elements in their standard states have heats of formation, free energies of formation that are equal to 0, just like heats of formation for elements in their standard states is also 0. The entropies for elements in their standard states is not equal to 0. Okay, so everything has entropy, especially unless we're at 0 Kelvin and a pure solid. Okay, so these are not equal to 0. These are equal to 0. And again, because this is a state function, we can actually get the free energy change of a reaction by doing the sum. Are you tired of this equation yet? Of the moles of the free energy change of formation of the products minus the sum of the moles of the free energy change of the reactants. Remember, we did this for delta H. We did this for delta S. It's just another way to predict the spontaneity of the reaction by looking at the free energy change of the formation of the products versus the free energy change associated with the formation of the reactants, and that delta will be your delta G of the reaction. But again, we don't use that one as often as we tend to use delta G is equal to delta H minus T delta S. There will be some really annoying problems where you have to use heats of formation. You have to use like these guys to calculate that. And then you have to use these guys to calculate that. And then combine those to calculate that, right? So if they don't give you the actual heat of the reaction or the entropy change of the reaction, you might have to go back to Appendix C. And I think I did assign a problem like this just for fun, where you have to go back to Appendix C and you have to do heats of formation of the products minus the reactants to get delta H, do the same thing for delta S, and then plug those two values in to predict delta G. Of course, there are values for these, standard free energy changes of the substances also in Appendix C. So you can use this reaction as, or not reaction, you can use this equation as well. So calculating this and calculating that, same thing, same value, amount of free energy change associated with a reaction, but just two different ways to calculate it. I don't think we need to practice one of those here in this lecture, but there is a problem like that that you guys can do on your own. Yeah, so I don't think I put anything there because that's just tedious. Don't forget your moles, watch your units. Okay. So moving on to our last little bit here. How is it that free energy changes or is related to temperature? So remember that fun little exercise we were sort of doing at the beginning of this lecture where I said, if this value is negative, favorable, and this value is positive, which is favorable, this reaction will always result, or this set of circumstances, I'm sorry, will always result in a negative delta G. This will always be spontaneous. And then we said, well, what if, delta H is positive, not favorable, and delta S is negative, not favorable? That will result in a reaction that is always not spontaneous, right? So this is going to be always spontaneous, and this is going to be always not spontaneous. But like we saw in the quantitative practice problem that we did, we could have situations where one of these things is not favorable, like a positive delta H, but the delta S is also positive, which is favorable. So not favorable, favorable. What's going to happen in terms of delta G? It's going to depend on temperature. So if we want to think about, well, what would result in a spontaneous reaction or a negative delta G? If we're looking at these signs, the delta G is going to be negative when temperature is high, right? Like if we have a big value for temperature, we're going to get a negative delta G over here. So this will be spontaneous at high temperatures. This is just a fun little logic exercise. And if we're looking at the reverse scenario where, like, let's say this reaction is exothermic, which is favorable, but it decreases in disorder or increases in order, which is not favorable. You can see here, we're going to end up with like a positive value here. And so like what's going to result in a spontaneous reaction in this scenario if temperature is low, right? When we have low temperatures, this factor is going to be smaller, and thus this negative will prevail, and we will end up with a spontaneous reaction. So this will be spontaneous at low temperatures. Okay, so that is how this temperature factors in to whether or not a reaction is going to be spontaneous or not spontaneous. Any questions? Haha. All right. Whoa, I left way too much space. Why did I leave that much space there? I must have wanted to talk about something else. Let me refer back to my notes to see what else I wanted to talk about. Positives, negatives, yeah. I didn't want to do another practice problem. Okay, I guess I just left too much space. All right, so now let's take a look at our final piece of thermo that we need to discuss in our little mini look at thermodynamics. And that is how free energy relates to equilibrium. So remember we were talking about like the ball rolling down the hill, and that when the ball settles down at the bottom of the hill, this is where we are at equilibrium, right? So when delta G is equal to 0, the reaction is at equilibrium. It's going in the forward and reverse directions at equal rates. So, why do we care? We care because this is a hard one for me. Why do we care? We care because this is actually going to help us make predictions about the direction that the reaction is going to proceed spontaneously in order to achieve equilibrium. And it's going to, oh, sorry, I didn't silence my phone. I hope you guys don't hear it dinging. Oh, Miss Schmidt wants something. Oh, good. She's going to use the same tablet and stylus that I'm using now that I'm good at it after I bought a bunch of crap that didn't work. Okay, sorry. So anyway, it's also going to help us make predictions about how long a reaction is going to proceed before it reaches equilibrium, which you might not understand why we care about that until we talk about electrochem. It's basically going to help us determine like the life of batteries, like how long is this battery going to operate? Because once that battery gets to equilibrium, the reaction is not going to proceed anymore. So I guess that's why it was hard for me to explain why we care, because we actually haven't looked at applications of this yet, but we will. Okay, so first thing I want to talk about is delta G at standard conditions, like we were talking about before. Remember, standard conditions being 298 Kelvin, 1 atmosphere of pressure, and 1 molar concentration if we're talking about solutions. So again, we don't have to derive this, but we can actually get delta G if we are at non-standard conditions. If we take the delta G under standard conditions and we add to that R, T, ln of Q. Remember, Q is basically the same thing as our K if we are at equilibrium. So remember, it's just that equilibrium constant expression. Remember, KEQ is your products raised to their coefficients over your reactants raised to their coefficients. So this R is your energy R. Remember your 8.314 joules per mole Kelvin. T is obviously your temperature in Kelvin, and Q being your equilibrium constant expression, but not necessarily at equilibrium. Now, if we were at equilibrium and if we were at standard conditions, all of these values for concentrations and pressures, they would all be equal to 1, right? Like if we were at standard conditions, that would be the pressures that we would plug in here if we were talking about Kp, and this would be the concentrations we would plug in here if we were talking about Kc. So if all of these values are equal to 1, then your Q is going to be equal to 1, right? Q would be equal to 1. And we all know that the natural log of 1 is equal to 0. So that makes this whole thing essentially equal to 0. So then delta G under not standard conditions would equal the delta G at standard conditions, which makes sense, right? So like if we were at standard conditions, these two things would be the same. But if we are not at standard conditions, then forget about that. Then we can just go ahead and use this factor to figure out what the delta G would be under non-standard conditions. Okay, now there's something else that we can do with this nifty equation where we can actually see how, in fact, delta G, or the free energy available for the reaction to proceed, relates to our equilibrium constants. So let's just do a little derivation here for fun. If we are at equilibrium, remember your delta G will be equal to 0. So we're going to plug in a 0 there, and we're going to relate that to our delta G under standard conditions and add to that R, T, ln. Now we're not going to use Q this time because we're at equilibrium, so we're going to use K. If I want to rearrange this equation to solve for K, I could say that delta G naught is equal to negative RT ln of K. And now I want to solve for ln of K. Ln of K is going to be equal to my delta G naught over RT. And if I want to solve for K, remember I'm just going to anti-log that. So K, or anti-natural log, I should say, my bad, which is E, remember E, to the negative delta G naught over RT. And you're like, why do I care? Well, you should care because it's another way to solve for your equilibrium constant. It's another way to solve for KEQ. So instead of doing KEQ is equal to, your reactant concentrations and your product concentrations up here, you instead, if you know the standard free energy change for the reaction and you know the temperature that the reaction is at, you can actually calculate K. And you're like, why do I care about K? Well, remember, big Ks that are greater than 1 means you've got more products at equilibrium. And if Ks are less than 1, you have more reactants at equilibrium. And if K is equal to 1, you have the same amount of products and reactants at equilibrium. So it's kind of cool, you can sort of like look at the potential that the ball has for rolling down the hill. This is my analogy for delta G. If we know how much potential that reaction has to proceed in the forward or in the reverse direction, we can actually calculate the equilibrium constant from that. And then that equilibrium constant will tell us what we have more of when we do achieve equilibrium and the ball settles down at the bottom of the hill, or the reaction's going in the forward and the reverse rate at equal speeds. So this all sort of ties together. And again, this, spontaneity of reactions and which direction they are going to go in order to achieve equilibrium is going to be really important to us when we look at electrochemistry and how we get batteries to operate spontaneously. How do we spontaneously get energy from two different substances put in series with one another? It's kind of cool. It's one of my favorite units. So I'm a little sad that we don't get to cover it in class together. But we'll just keep doing it virtually. Hopefully that lecture was better than the last one. I guess I don't have anything left to talk about here. All right, you guys. So I think I assigned some problems and some reading with this section of the thermo lecture as well. And as Savannah would say, be sure to smash that like button and subscribe to my channel. I don't even know if you can. I'm not sure how my YouTube channel is set up. Hopefully this even works. All right, you guys. Until next time.